Hey everyone. So this week we're going to talk about the topics of acceleration and gravity and how those interact. Okay. So first let's start with the concept of acceleration. The definition is the rate of change in speed with time. A more simplified version would be the rate at which an object changes its velocity. Right. So keyword would be change, right? The change in velocity. Or even simpler put, is just how fast is the speed or velocity changing, right? So it implies that it is not a continuous speed, right? Up to this point, we've been talking about constant speed, right? When we did those mathematical problems, it was just an average speed during a certain amount of time. And this is going to look at an increase in speed, or you could actually have a decrease in speed, right? You could have negative acceleration, right? Or what we would call deceleration. But again, it's just a change in speed at this point. Now, again, because we're working with algebra and mathematical problems, the symbol for acceleration is A, right? So easy to remember, A for acceleration. So let's talk about the equation, okay? The equation is A equal final velocity minus initial velocity divided by time, right? I'm looking at this in red. So again, VF, you'll see that often. Sometimes I see V1 and V0, but again, just to make it more simple, VF is the final velocity, and then you subtract VI, which is the initial velocity, and divide it by time. Okay, so you need to have two speeds in order to formulate for acceleration. You need to have a final speed, and you need to know the initial speed, and then how long it took for that change to happen, and that will give us our acceleration. Now, the units of acceleration are what we call meters per second, or more commonly, meters per second square. So again, note that there are two time intervals. And the reason is because there are two velocities, right? So, we square the seconds, or we basically, we'll always have a square of a time. Another common unit could be miles per hour per second. So whenever I give you examples, I often use cars or, people, and really the most common way to measure speed in this country is miles per hour. So I'll often refer to miles per hour per second. But again, it's very important that you note that the units sound like velocity units or speed units. However, there's a big difference. If you're ever told that something is traveling at or traveled at miles per hour per second or meters per second square, we're talking about acceleration and not speed or velocity. All right, so let's do a problem together. It says here, if a car takes 5 seconds to increase its speed from 30 miles per hour to 50 miles per hour, what is its acceleration? All right, so this is what we know, right? If it went from 30 to 50, we know the final velocity is 50 miles per hour, correct? And we know that we're going to start measuring at 30 miles an hour, okay? Sometimes it'll say things like from rest or from a stop. If you hear that or you read those words, then you know your initial velocity is 0. But in this case, it's not. It was going from 30 miles an hour to 50 miles an hour. So we have our final velocity, our initial velocity, and we're given time. And again, the question is, what is its acceleration? So again, we are adding equations to our equation bank, right, in which we should be memorizing these equations, right? So we have v equals d over t, right? And then we can obviously use algebra to solve for any of those three variables. Well, now we have another one. It's A equals final velocity minus initial velocity divided by time. So now it's a matter of just plugging in the numbers, right? So we know 50s are final, so we put that first. It's very important. A lot of people, this is the mistake they make, is they flip-flop these numbers. They want to put the initial velocity first and then subtract the final velocity, because that's the way it's given to us, right, in the question. However, it's important that you note that the final velocity is the number you start with, and then you're subtracting the initial velocity, okay? And again, it should be a smaller number if it's an acceleration that's increasing. But again, you could have an initial velocity that was faster than your final velocity, right? It's just gonna, it's just a matter of understanding where you started and where you end. So again, 50 miles an hour minus 30 miles an hour divided by 5 seconds. Again, do not, when you're writing math problems in your notebooks or wherever you're answering questions, don't get rid of the units. That way you don't you don't forget what the final answer unit is going to be, right? So we have an easy mathematical problem here, right, as far as the numbers go, because you get 20 miles per hour divided by 5 seconds. Again, the first thing I look is, do any of these cancel each other out? And the answer is no, because you have miles per hour and you have seconds, so they cannot cancel each other out. This is easy though. 20 divided by 5 will give you 4, right? So we go back down and we simplify. 4 miles per hour per second is our answer, because again, this can no longer be simplified. So our answer is that the acceleration is 4 miles per hour per second. Okay, or you could give it to you could give an answer in a fraction like this, right? The important thing is, again, if you notice, there's 2 hour units. There's the hours in miles per hour, and then all that is divided per second. Because what this is showing me is that if I had a timetable of its acceleration, right? If I plotted this person's speed through time, I would start at the first second, or 0 second. At 0 is 30 miles an hour, correct? And then at 1 second later, it's 34 miles an hour, right? Because every second it's accelerating 4 miles per hour faster. So that means at the first second mark, you would be 34. At the 2 second mark, you would be at 38. At the 3 second mark, you would be at 42. Get it? I'm increasing by 4 miles per hour each second. So again, I'm not always driving at 30 miles an hour, right? I'm accelerating. So at 3 seconds, again, I'm at 42. At 4 seconds, I'm at 46. And at 5 seconds, which is what it said it took, right? 5 seconds, you would be at 50 miles per hour, right? So again, I'm plotting the speed at different time intervals. And again, the speed is increasing 4 miles per hour each second. And it does, sure enough, it takes 5 seconds to go from 30 miles to 50 miles an hour if I'm increasing by 4 miles per hour each second, right? So that's kind of how I double check my answer. All right, here's another question. Again, you're not always given the questions are often for you to solve for different variables. That's how physics works. So this question says, starting from rest, and again, that's a clue, starting from rest, your new truck accelerates at the rate of 5 miles per hour per second. Okay? Again, start paying attention to when you're given units so that you can extract the correct information. So yeah, it accelerates at a rate of 5 miles per hour per second and continues this acceleration for 8 seconds. What will the speed be at the end of the 8 seconds, right? What will the speed be at the end of 8 seconds? So the first question again is, before you look at any of this in red, the question is, what am I being asked to solve? Okay? And so the question says, what will the speed be at the end? So that implies that it's the final speed, right? At the end of the 8-second run, that's my final speed. So I need to solve for VF. Now, even if you didn't know we were talking about acceleration, the word acceleration comes up, right, a couple times here. So I know I'm going to use this equation, all right? But then I need to solve for this variable. Now the other question, or the other answer that I'm giving, or the other variable, is it says starting from rest. So what is my VI going to be? Yeah, it's going to be 0, correct? If you're starting at rest, you're 0. So guess what happens to this variable? Anything minus 0 is just that, same variable. So I can cross it out and make this even simpler. right? So I got rid of this variable because it's 0, and all I'm left is final velocity divided by time. Okay, well, again, I need to keep this by itself and add, make t go on the other side. So I'm going to multiply by the reciprocal of 1 over t, right? So I'm going to get t over 1 on this side, and again, it cancels out my t, my time, and then since I multiply by t over 1, which is just t, I add that onto my other side of the equation. So again, I have final velocity equals, right, the acceleration, which I need on one side, multiplied by time. Because again, I had to on this side of the equation, I had to multiply by the reciprocal of 1 over time, because time's in my denominator, right? So I did the reciprocal of 1 over t. So again, the final velocity is going to be equal to my acceleration multiplied by my time. That's how I'll know what the final speed is, right? I need to know how fast I'm accelerating and how much time I'm accelerating for. So again, that's perfect because I'm given those things. I'm given the acceleration rate, right? Because miles per hour per second is a unit of acceleration, not of initial speed, not of final speed, but of the actual acceleration through time. And I'm given that it happens for 8 seconds. So I have 5 miles per hour divided by a second, right, per second, multiplied by 8 seconds. So again, the first thing I note is that I have a second unit on the numerator, right, because this isn't a fraction, so I can always just imagine this being over 1. So this is on top, and I have seconds on the bottom of a fraction here. Okay, that's why I like to, again, write down my units. So I know that my seconds will be crossed out, and my answer is going to be left in miles per hour, which is great because that is a unit of speed, right? So again, now it's just a simple multiplication. 5 times 8 is 40. And again, I'm left over with the units of miles per hour. So that means my final velocity is going to be 40 miles per hour. And again, I can sort of plug this back in. If I go at 40 miles per hour and subtract 0 and divide that by 8, I'm going to get an acceleration of 5 miles per hour, right? That means I started at 0 miles per hour and I accelerated at 5 miles per hour each second, right? So I'm plotting seconds. At 1 is 5, at 2 is 10, at 3 is 15, at 4 is 20, right? 5 is 25, 6 is 30, 7 is 35, and 8 seconds it's 40 miles per hour. Okay, so that's how you get from 0 to 40 miles per hour in 8 seconds, is by speeding up 5 miles an hour each second. Okay, so hopefully that shed some light on that. We're not going to talk about gravity, okay? And I don't know, I like movies, so I'm always adding pictures like that. So we know that the Earth is surrounded by its own gravitational field. And again, we're not going to go really deep in this. I just want to explain a couple of facts, right? This gravitational field, right, which is tied into its mass, right, how much mass the Earth has, this exerts a constant force on all objects towards it, right? So it's an attractive force towards the Earth. That's why when we jump, we fall back down, right? That's why the apple falls from the tree and never up or sideways, right? So it was found that any falling object will accelerate towards the Earth at the same rate, okay, regardless of its mass. Okay, and I don't know if you've ever heard of Galileo's falling bodies experiment, where he proved to people that you could have, say, a bowling ball and a tennis ball, and if you drop it from the same height at the same time, they will hit the ground at the same time. Okay, now again, this obviously doesn't take into account things like resistance, wind resistance, right? So obviously, I have a slide about the hammer and the feather. Those two objects don't fall at the same rate, but it's not because of their weight. It's rather because of their shape and the way they catch air, right? Well, I'll talk about it in a little bit. So again, for thousands of years, people just erroneously thought that heavier objects fall faster than lighter objects, because when you're just traveling down the road, it is true that the heavier the object, the more speed it has, and the harder it is to slow down, right? And we'll talk about force next in a few weeks, but as it pertains to gravity itself and falling objects, it's clear that in the absence of air resistance, gravity causes all objects to fall at the same rate. So when gravity is the only force pulling an object and causing its motion, then it attracts the same force to any object, whether it's a feather or a hammer, right? Again, the problem is air resistance. So if we try this experiment, right now in our backyards, the hammer is going to fall first. But again, if you remove all air, and it has been done, there's YouTube videos all over it, of hammer and a feather being dropped in a vacuum, meaning in a place where there is no air at all, they do fall at the same time. And this is also famously televised by Apollo 13 on the moon, right? So the first astronauts that landed on the moon actually did this experiment on the moon back in this 69, and again there's no air in the atmosphere of the moon, and again both the hammer and the feather fell at the same time. Okay, but again this just kind of proved Galileo's concept of gravity and its force. So let's talk about acceleration of objects as they're falling, right? Or acceleration of gravity. So let's start with the law of acceleration of gravity, and it's in bold because it's important. It's something that you're going to have to memorize. And this law simply states that an object falling freely near the Earth's surface increases its velocity. That means it accelerates. That's why the word acceleration is in the name of the law, right? It accelerates at a rate of 9.8 meters per second for each second of its descent. And again, this is so important that it's given its own variable. The variable is simply the lowercase g. So if you see the lowercase g, it stands for acceleration of gravity. And again, this isn't really an equation; it's more of a statement, right? It means that the acceleration of gravity of falling objects, and we know that it doesn't matter the mass, right? It doesn't matter the weight. If you remove air resistance, all free-falling objects near the Earth's surface travel at 9.8 meters per second square. Again, so that it explains that it's an acceleration and not a constant speed. So that means that objects, as they fall, they don't travel at the same speed. They actually increase in speed. And they increase in speed at the rate of 9.8. So this was found out. So what does that look like? I have a little bit of a diagram. So imagine we're off the Leaning Tower of Pisa, right? And we drop a ball, right? So we know that as we hold it, just before we let it go, we're going to call that time zero. And if you multiply 9.8 meters per second times zero, you get zero, correct? But as it's falling for 1 second and we clock its speed, we will see that this ball is traveling at 9.8 meters per second. Okay, that is its velocity. And that is because it's accelerating at a rate of 9.8, right? If we continue, this ball continues to fall, at the 2-second mark, it's going to be traveling at 19.6 meters per second. So it's speeding up. It's accelerating. All right, and we know that it's accelerating at the rate of 9.8 meters per second square. So at 2 seconds is 9.6. And then at 3 seconds, if it continues to fall, if it's a really tall tower, right, and it's falling for 3 seconds, right as it's about to hit the floor, it's clocked at 29.4 meters per second. And again, how did I get to that number? Is simply put 19.6 plus 9.8. Okay, when we teach this to kids in middle school or high school, sometimes they'll just round to 10. But again, we're all college students, so we're going to use the correct number, 9.8. All right, and again, so this shows us that as objects fall, they don't drop at a constant speed. They actually accelerate. Okay, so they travel faster and faster the longer they're in free fall. So again, we're able to subtract both velocity information, but we can also subtract distance, right? Because if you remember from last week, you could solve for speed by dividing the distance over the time, or you can solve for the distance by multiplying the time by the speed, right? So we could use algebra and formulate for distance. Well, the same holds true here. So let me start here with the velocity. Again, to reiterate, free-falling objects are in a state of acceleration, right? So it's not a constant speed, it's an acceleration. It increases at a rate of 9.8 meters per second squared, or 9.8 meters per second per second. The velocity of a free-falling object that has been dropped from a position of rest, right? So this doesn't take into account if you throw it up in the air. So it's important to understand that this is just dropping it from rest, is dependent upon the time that it has fallen. Because we know that if it's been only 1 second, the speed is 9.8. But if it's been 3 seconds, the speed is 29.4, correct? So it's depending on the time. And so the formula for determining the velocity of a falling object after a certain time, right, we're going to call that t, is Vf, right, which will be our final velocity, equals the acceleration of gravity multiplied by the time, right? And that makes sense. That's what we did here. You take 9.8, multiply it by 3, and you get 29.4, right? So that's not, I wouldn't really call this a new equation to memorize. I think this just explains how I got these numbers in a much simpler way, right? So we're not just adding, right? I could say that the next interval is going to be 10 seconds, right? And you're going to know that it's 98.0 meters per second. That's going to be the speed, right? Because you can multiply 9.8 times 10 in your head. So that's what I'm doing here on this left side. Okay. Now again, from this, we can formulate for the distance it traveled, right? So what if I want to know how tall this building is based on how long it fell, right, and the speed? Well, the distance that a free-falling object has fallen from a position of rest, again, is also dependent upon the time of fall. Now we're going to see that the time plays a different role here, though. And this distance can be computed by using, by the use of the formula. And the distance falling after a time of x seconds, right, whatever amount of seconds, is given by the formula of d, which stands for distance. D equals 0.5. That's a constant, right? So this never changes. So 1/2, 0.5, times the acceleration of gravity, times the time is spent in free fall, square. And again, this is very important. So if you just multiply by time, you will get an erroneous answer. It's multiplied by the time squared, which tells us that the time is going to play a bigger role, right? Because when you square something, it doesn't just double, right? It's not times 2, it's time itself. So it's its exponent. Let's do an example together to show our understanding. All right, so if we use the previous diagram, right, that leaning tower, when the ball has fallen 1 second, how far, right? When I say how far, you understand that I'm talking about distance. How far has it fallen? So again, this is my equation. I always start with the equation. D equals 0.5 times acceleration of gravity times the time squared. You have to memorize this. All right, guys? That's another one you have to memorize. So again, now I'm going to plug in the things I do know. So this is a constant, so this just drops down here the same. We know acceleration of gravity is 9.8 meters per second squared. So that drops down here. These are both constants, correct? And then here, time, after 1 second, is just simply 1 second squared, right? So what's 1 second squared? It's 1, right? 1 times 1 is 1. So that makes it simple. And you have 0.5 times 9.8. So simply, basically, multiplying by half, right? So you get 4.9. 4.9 meters per second squared multiplied by 1 second squared. Again, the first thing I notice is that I have a second squared on the top, and I have a second squared on the bottom, on the numerator, right? Because it's meters per divided by second squared, so this is at the bottom. So I'm going to cancel out the second squared and the second squared. I'm going to be left with an answer that only has meters. So I have 0.5 times 9.8 is 4.9. 4.9 times 1 is 4.9, correct? So my answer is 4.9 meters. And again, to me, it's very important that you have the units. Distance is going to be measured in meters or feet or centimeters or kilometers, right? But since we're just dealing with standard units, right, of meters and seconds, our answer should be in meters. And again, you don't have to memorize that, because again, if you left your units and you've cross multiplied and simplified, and you know how to do that, you can know that you have to cancel out the second squared. All right, so my answer is 4.9. Again, that one's simple, right? After 1 second, this is basically what I'm saying. The distance between here, this ball, this height, and this height is 4.9 meters. Okay, that's how far it fell after 1 second. So what about after 3 seconds, right? It just keeps going, it keeps going. What if I want to know the distance between this, the top of the tower, and this? We're just going to call this the bottom of the tower. Knowing that it fell for 3 seconds at the rate of 9.8 meters per second squared, what will the distance be from here to here? Well, we use the same equation, right? That's down here. D equals 0.5 times acceleration of gravity times the time squared. Again, this is a constant. This is a constant. But now I'm going to leave 3 seconds squared. And 3 seconds squared is 9 seconds squared. Correct? 3 times 3 is 9. So now I have 4.9 meters per second squared times 9 seconds squared. Again, we know that this will cancel each other out, the seconds. 4.9 times 9 is 44.1 meters. Okay? So that means that the distance from here to here is 49.1 meters per meters, just meters, 49. Okay. So again, notice that after 1 second, we only went about 5 meters, but 2 more seconds later, we're not multiplying by 5, right? Because it's not a constant speed. So our distance has increased dramatically. It went from 5 to 44, right? So again, if I put this all together now, this is what it's showing. At 0, it's the speed and the distance is 0, right? At 1 second, it traveled at a speed of 9.8, and it covered a distance of 4.9 meters. At 2 seconds, it doubled the speed, 19.6, but it's squared, right? Quadrupled its distance, right? Notice how the speed doubled, but the distance has increased way exponentially. And again, that is because time is squared. And then 1 more second later, it more than doubled, right? It went from less than 20 to 44. Even though only 1 more second, passed by, the distance is exponential, okay? And that is because of that relationship, expressed by the equation, okay? So in summary, right, we've learned about acceleration, and we learned a new equation that you're going to memorize, right? The final velocity minus the initial velocity divided by the time will give us the acceleration. So we need to know 2 time intervals, right? 2 speed intervals, I should say, and how much time happened between them. And of course, we can solve for any of these variables using algebra. We've also learned the law of acceleration of gravity, which states that all objects accelerate towards the earth at the same rate, and that rate is 9.8 meters per second squared. So that's a very important number, right? Very important concept. And from there, we can know how fast something is traveling at a specific time, right? And we know the speed of an object if we know the acceleration of gravity, that's for sure. If we just know how long it's traveled for, we can tell you what the speed is going to be, because it's going to be 9.8 meters per second multiplied by the time. And lastly, we're able to solve for distance, right? We could also tell you not just how fast it traveled at a certain time, but how much distance it covered, depending on the time. And we learned this equation, which is also very important. The distance is equal to 0.5 times the acceleration of gravity multiplied by the time squared. And again, when we looked at this, we noticed that the distance is exponential. It's not linear, right? It's not just going up in a steady plot. It's actually increasing by big jumps because the time is squared. All right, guys. Good luck this week. Again, email me. There's also a those the boards, right? Where we can write any questions for the class. All right, so you can communicate with me through that. I'm checking those as well. Have a great week. Bye.